No. He has changed his major to pre-dent, and he is doing the dental test thing today, and he's been studying since fall break for that.
So
yeah.
after today, he might be in class.
He should be back in class after that.
If we completely forgot to make a 30-second video saying, "Oh, Austin, we forgot."
Yeah,
You know,
he's
he's
thinking
going
about
to hear
that.
this entire recording, so he's probably going to watch this later.
Yeah, well, he knows that we care about him then. Okay, verify that H is a normal subgroup. Unless, of course, I cut it out. But. So we're going to consider the value 3 in H. And we're going to look at x plus 3 plus x inverse for all x in, yeah. So let's just look at it. When you're looking at 0, what is 0 inverse, by the way?
0.
So 0 plus 3 plus 0 is equal to 3, which is in H. Check 1. 1 plus 3 plus, what is 1 inverse in Z6? Except add 6 to it and you get plus 6 is 5.
Oh.
Because it has to be in Z6. It has to be listed in the set of integers from 0 to 5. So the inverse of 1 is 5. So we have 1 plus 3 plus 5. What does that equal to?
Wait, hold on.
9, which equals 3.
Why is the inverse of 1?
Okay. Yeah, 1 plus 5 is equal to 6. But remember, this is mod 6. So that is equal to 0. So what is this? This is 1 plus 3 plus 5.
9 which equals 3.
Yeah, 9 mod 6, which goes to 3 because we're dealing in Z6. But tell me, is 3 in H? Yes, it is. It's going to. 2 plus 3 plus, what's the inverse of 2 mod 6? 4.
I mean, it's not.
That's You like 12 today. Okay, so 5 plus 4 is 9. Mod 6 is what? 3. That's in H. How about 3? What's the inverse of 3? 3. So that's equal to 9 mod 6. It's still equal to 3, which is in H. And then 4. Notice 4, the inverse of 4 is going to be what? 2. So that's equal to 9. Yeah, we have to check them all. Yeah, because it says for all x, x inverse, so you have x, a, x inverse. And if you didn't know it was commutative, you'd have to check them all. So if you recognize it's commutative, you don't have to check them all. But, you know, I'm well on their way. So you either have to say, note that the Z6 is commutative under addition, and therefore we only have to check half of them, or you have to check them all. Yeah, but you need to recognize that when you do it. You have to say it, yes. Otherwise, I don't know that you recognized it, and I don't know you're making a mistake. So, yes. And then the last one, just because we want to cover them all. 5 plus 3 plus 1 is equal to 9. Mod 6 is equal to 3, which is in H. So, we don't have to do 0 because 0 plus anything is anything, and that just leaves you that, yeah. We'll look at that. If you do x plus 0 plus x inverse, that is going to be equal to x plus x inverse, which is equal to 0, which is in H for all x in G, which is our Z6. So what's your conclusion? H is a normal subgroup.
For this, wouldn't you, like, for a real proof, or if it's a normal, would you have to do 0 as well? Like 0 plus 0 plus 0, and then 1 plus 0 plus 5, 2 plus 0 plus 4.
Yeah, but that's the same thing that I
Oh,
did
that's what
right
we
here.
did, okay.
Yep, this is for all, yeah. So yeah, you do have to check it. I should make this a proof, shouldn't I? Because I think your homework says show.
I don't know what it's like.
There we go. Here's my... Okay, so now you know that H is a normal subgroup of Z6. Now the solution is in your book. This is the beginning example for section A, and they have made the table for you, so just check the table in the book to verify your results. This is a section A example before the problems. They actually did not prove that it was a normal subgroup. You have to verify that before their table identities work. Okay, A2 is one of your homework problems. And you guessed it, it's looking just like what we just did. On page 71 or 72. Yeah. So you have to go back and look at that one, and go ahead and work through that one together in your group and see what you get. Let's pause this. It's a great test question. This right here. It says number 4 on it. So show that H is a subgroup of G. It's a great test question. It's really not that hard to do. It's about 3 or 4 lines. How do you show that something is a subgroup? You guys remember that part? Close under inverses and close under the operation. So you have to show 2 things. And notice what they tell you. They tell you that G is a billion, and H is all the elements of G that have finite order. So you just have to take any 2 elements of finite order, take the product of them, and show that the product has finite order. The order is just going to be the product of the orders of the original elements. It's going to be less than or equal to that value, so you know it's going to be finite order. And then the inverses are in there, which is also a similar approach. You just take an inverse from G and realize that the order of the inverse is the same as the order of the original element, and you're done. So attempt that one on your own. That one's a great one for a test question. Combines so many different things together. It's just a wonderful question. And let's look at E number 6. This is actually a homework problem for you guys.
Dr. Anderson,
Yeah.
did you say that number 4 was in the reading?
Yeah, it's in the reading, but they actually didn't prove it. They said it's left to the reader. And anything that says it's left to the reader means it's going to show up sometime for you guys to see again. Well, either that or you get to practice and you show it to me, one way or the other. But let's look at your homework question number 6. So it says let G be a group and H a normal. What is that? I thought it was on the list. I have it circled in my book, so it meant to be on the list if it wasn't. You do E5? Oh, we're going to do number 6 then, even if it isn't on the homework. It's a good one. So let G be a group and H a normal subgroup of G. And here's what it says. In the integers, the rational numbers mod the integers. Oh, that's fine. Show that every element has finite order. How do you show that something has finite order? How do you show something has finite order? What does it mean for something to have finite order? Yeah, the order isn't infinite, but what does the order of an element tell you? That is actually a profound statement. Yeah. X to the power equals the identity, whatever power it is. And if it's infinite power, then it's that means no finite integer has that property. But if it's finite power, then there exists a finite integer, so that x to that finite integer equals the identity.
But we don't know that finite.
Yeah, but we're going to figure it out.
This is very fast.
We'll do it slowly. So let's consider our quotient group Q mod Z. If we take an element in Q mod Z, what does it look like? Q's are rational, those are fractions, so to speak.
So like 4 divided by 4, would that be in Q?
Well, that would be in Q, because that's fraction. Anything that you can represent as a fraction is in Q, so all your integers are in Q. Yeah. You can write it as a fraction.
It's not even that good to put that because it's over.
But remember, we're not actually doing the division here. This is our group, so we have to actually, let's figure out what this is going to look like.
Is the operation still additional quotient?
We're still dealing with addition. So let's pick out some integers. So yeah, we're taking the integers and we're adding a fraction to it. Yeah. For each AB in the integers with B not equal to 0, right? So we have fractions. So we're taking our set of integers and we're adding a particular fraction, and that gives us a particular coset. Now, we want an element. It says the elements in Q mod Z have finite order. So that means we're looking at the set of the integers plus a fraction, and we want to know that that's going to have finite order. That means we have to be able to raise it to some power and see what happens. So let's let Z plus A over B be an element of our, it's fascinating, because I can do control B with the left hand side. Maybe it's just the right hand control that gives me the degree. I don't know. I don't know my computer. Yeah, exactly. Okay, so Z plus A over B is going to be one of our cosets. Now, what do I know about my fractions? How do I get a fraction into an integer? Maybe I should ask you that question. It'll be a little bit better question. You multiply, add it to itself B times. Okay? Note that A over B plus A over B, how many times? B times. Let's see, where's my dots? I'm not showing normal, I'm assuming normal in this case. I'm not showing normal, I'm assuming it's normal. Yeah, it's in the, yeah. Let G be a group and H is a normal subgroup. So in this case, G is the rationals and H is the integers.
I don't get how that's a response to what I said.
You are asking about inverses. Inverses are part of what you show for normal.
No, I said you could add a fraction to some B amount of times, but what about adding its reciprocal to get to an integer with my first stop?
Oh, I see where you're going with that. It takes you to 0, but it doesn't get you to just an integer. But that, I don't know. Let me think about that, if that'll actually get you where you need to go. Let me show you where you need to go, and then we can think about it. Yeah. Well, you're multiplying by it. To get to 1, you did.
I wasn't thinking I did.
Oh, okay. Well, then you meant to say 0 and not 1. Okay, so we have our fractions here, and we've added them together n times. Let's put our decoration in here. Yeah, the Christmas decorations are out in stores. And that's sad because it's not even Thanksgiving yet. Where is it?
You want to be next to the sigma at the top, next to the tilde percent. Right, that's below, below.
Oh, yeah, sure enough.
Oh, label.
Yeah, the label. Okay, so this is b times. So that is equal to a. A has to be in the integers, right? So then when we actually take our coset, now we're using our notation here. Even though I'm putting it as the power b, that means I'm adding it together b times. Yeah, operations addition. So I don't know what that just did. There we go.
I have a question.
What's your question?
You said something earlier that didn't make sense. You said we're not assuming that it's normal, we're showing that it's
No, I'm assuming that this one's normal. Z is a normal subgroup. Yeah. Under addition, it's a normal subgroup. But what is this equal to? Since it's a normal subgroup, this is the integer z plus a over b added together b times, right? Does that make sense?
No, why isn't it b times the integer?
Okay, when we have, think about this, HA operating on HA, our book said this is HA operating on A, but that's HA squared. You're just combining these guys together, you write H down once. So that's all I did.
Oh, I get it.
Yeah,
The same thing we did before that.
the same thing that we did before. Mhm.
So ha equals ha.
Yeah, exactly. Don't forget that now.
Is it the same thing as the generator being separate numbers, like right above on the board?
Yes, that's exactly what's
Did you notice
happening.
like throughout the
It's
whole
just
thing,
that those
it
were
was
numbers.
ha, and like
Mhm.
e, and it was like
So tell me what this is equal
like,
to
yeah,
then.
H on element
Z plus A. But when you add an integer to all the integers, what do you get? Integers. So what we have just shown is if you do Z plus A over B to the B power, which is a non-zero integer, that's equal to the set of integers, which is the identity of the cosets, because it's Z plus 0. That's our identity set in our set of cosets. So that the order then of our set Z plus A has to be less than or equal to B. It could be that there's a smaller integer that works to cancel it.
Why not just equal a lot less stuff?
Because I don't know, the order definition is the smallest positive integer, so that takes it to the identity. It could be in our fraction that it cancels out. In other words, we could have part of B as a factor of A, like, I don't know, 12 over something that cancels with part of the 12, and so a smaller integer would make it go away sooner. Yeah. So if you had like a 3 and a 2 down here, and you had a 3 and a 4, a 3 and a 5 up here, and then if you multiplied by the 2, the 3 cancels with the 15, and you get something that takes it to an integer faster. I just didn't specify that they had to be relatively prime. If I did, then I know that B is the order. Yes. But what does this tell you? Every element of our class, of our rationals, I don't have the rationals written down. Every element of our cosets Q mod Z has finite order. Yeah. And we are done. Is that up far enough for you? Okay. Yeah, that was a fascinating little proof.